Hello, this is um this is chapter 8. We're going to be talking about probability, and we're going to start with 8.3, empirical and theoretical probability. Let me just get that a little bit thicker. Here we go. Okay, so an experiment is a controlled operation that yields a set of results. What we're doing here is we are defining um, some of the vocabulary so that we can move forward with, you know, and use this vocabulary. So outcomes are the possible results of the experiment. An event is a sub-collection of outcomes, and an empirical probability is the relative frequency of an event based on operations. So let's look at before we actually calculate this empirical probability here, let's look at some of these. So, for example, if we talk about rolling a die, a fair die, a six-sided fair die, our sample space is going to be 1, 2, 3, 4, 5, and 6. So again, notice that we are talking about a set. So that means that we are writing it inside the braces. Now, for example, if our we're looking at rolling less than 4, that would mean that our event would be 1, 2, and 3. Oops, I don't need a comma there. Or yeah. Okay. So when we calculate the relative frequency here, empirical probability, that means that we are taking the number of times event E occurs divided by the number of times the experiment is performed. Okay, next we're going to look at theoretical probabilities. So frequency is determined by a study of all possible outcomes. So that is our sample space S that we just wrote right here for rolling a die. Okay, so that probability we calculate by taking the number of outcomes in the event and dividing it by all the possible outcomes. So, for example, if we look at this rolling less than 4, we have 3 outcomes in that event, and all the possible outcomes, we have a 6. So we can simplify this to a half. Okay, next one is the law of large numbers. So probability applies in practice to large number of trials, not a single trial or a small set. Relative frequency in the long run is predictable. Okay, first or next, we're going to look at 4 important probability facts. So our first one is that probability of impossible, so it cannot happen, is going to be a 0. Second is possibility of a sure thing, so we know that it is for sure going to happen. That is 1. And then third is every probability is between 0 and 1 always. We cannot have negatives and we can't go over 1. Our fourth one is that sum of all probabilities, oops, that's a B, equals 1. So if we have the probability of event plus the probability of not the event, this is going to equal 1. So now, if we need to calculate the probability of the not event happening, we can just do 1 minus probability of the event. So, for example, if we do rolling A3, our probability of rolling A3 is going to be 1 out of 6 because we have 6 outcomes and only 1, 3. Now, if we need the probability of not rolling A3, so the event is not happening, we could calculate this by 1 minus rolling A3, which is 5 over 6, which we know already. So we are using this. This is called the complement. So we already know that there's 5 other numbers, so that would be 5 other outcomes out of the 6. So either way, when we get to the larger numbers, it's easier to use this, what's called the complement, instead of actually counting all of it. Okay, next we're going to go into looking at the empirical probability versus the theoretical probability, what the actual difference between those two are. So we've got an empirical probability here. And again, hold on a second. Yes, so empirical sometimes is called experimental probability. So notice that it can be an experiment, an actual thing that happens, whereas in if we look at the down here, theoretical probability, that's in theory it's going to happen. So this is calculated just like we did it on the other page. So number of outcomes divided by the number of trials. Okay, we have several friends went fishing and caught the following types of numbers of fish right here in that table. We're going to find each empirical probability. So we need first the grouper. So there are 13 caught, and we need a total so that we can calculate the probability. When we add all the fish that are caught, we get 55. So this 55 goes down here. We do the division and we get 0.24. Okay, let's look at sharks. 20 sharks out of 55. That's the total. And this simplifies to 4/11ths, which is 0.36. Next one is flounder. 3 out of 55, which is 0.05. And then we've got the kingfish, 19 out of 55, which gives us 0.35. Okay, next we're going to go ahead and calculate the probability of the grouper, which we're going to do 13 over 55 plus the probability of the flounder, which is 3 over 55, plus the probability of the shark, 20 over 55, and then the kingfish, which is 19 over 55. There's a reason why I did it. I did not use the simplified version of the fraction for the shark because now we can add easily because we have common denominators, 55 over 55, that equals 1. So in general, the sum of the probabilities of all possible outcomes is 1. Again, this, because we added all the possible outcomes over here, it should add up to 1. If it does not, something's wrong or there's a mistake somewhere. Okay, next, we're going to go ahead and review this, which we just did on the first page. So what is the probability of an event that is certain to occur? That would be a 1. What is the probability of an event that cannot occur? That would be a 0. So the probability of an event must be between 0 and 1. And if we add the probability of event plus the probability of not the event, it's going to be 1. And again, like I mentioned, these two are complements of each other. We call them complementary. Okay, next we're going to look at the theoretical probabilities. So this is something that can happen theoretically. So the probability of the event is going to be the number of outcomes divided by the number in sample space. So we use a little bit of a different wording here. We're still dividing, so the basic is the same. It's just that it depends on if we're using the empirical or the theoretical, what the wording is that we're using. Okay, so each individual letter of the word Tennessee is placed on a piece of paper, and all 9 pieces of paper are placed in a hat. If one letter is selected at random from the hat, determine each probability. So all of these are going to be over 9 because there's 9 letters in that word. Next, we're going to look at S. So how many S's do we have? We've got 1 and 2. So probability of S is 2/9. Now, the probability of not S, we have 2 different options. We can count the letters that are not S because there's not that many of them. So we get 7/9, or we could have done 1 minus 2/9, which is 1 minus the probability of S using that complement. We get the same answer here. Okay, probability of a consonant. So T, N, and S, we've got 1 T, 2, 3, 4, 5. So it's 5/9. Now, notice that what I'm doing here, there's different options with the probabilities. Here, I gave a decimal as an answer. That is one way to give the answer. Or we can leave it as a fraction, or we can convert it to a percent as well. So those are the 3 different ways of writing a probability. Okay, probability of T or E. So we've got 1, 2, 3, 4, 5 T's and E's, so T or E, and still 9 letters, so it's 5/9. Next, probability of W. Well, do we have any W's in the word Tennessee? No, we don't. So that's going to be a 0 over 9, which is 0. This is the probability of an event that cannot occur. Next, we have the probability of not V, Well, do we have any V's in the word Tennessee? No, we don't. So for sure, the letter that we're going to pick is not going to be a V. So this one would be a 1. Okay, next, we're going to look at um, a deck of cards. I'm going to show you a deck of cards here. This is a deck of cards. So it looks like this. Um, there's also the six-sided die on the bottom of this page. So we have um, the suits are spade, heart, diamond, and club. And then each one has 13 cards. So this is 1, 11, 12, and 13. It's right here are the number values. So each suit has 13, and we've got 4 suits. So we've got 4 times 13, which is 52 total cards in a deck. Total suits in a deck. That was our actually, I'm going to write them down here because it is asking different suits. So we have our diamonds and hearts and spades and clubs. So total suits in a deck is 4. And this next one says, and their colors. So I just did them in their colors. So these are red and these are black. Okay, next one. Total cards in a suit, 13. 1 through ace through king, which is 13. Different cards would be ace, which is 1. Then number cards 2 through 10. We've got the jack, we've got the queen, and we've got the king. So all of these can again be seen on this one here. Okay, next we're gonna do the probability. So one card is selected from a deck of cards, determine each probability. So probability of it being a 5, we have, if we go back here and look at, we've got all of these cards are 5s. So we're going to go ahead and write, there's 4 different possibilities for a 5, and that is out of the 52 cards that we've got in a deck. So this simplifies to 1/13. Okay, next one is not a 5. So we have the option of calculating all the other cards to see what that is, or we can do 1 minus 1/13, which is 13 over 13 minus 1 over 13, which gives us 12/13 as our answer. Or if we want to do it with the full deck 4 and 52, it would be 48 over 52. And that simplifies to 12/13. Your calculator simplifies it with the fraction button. Okay, next one is 5 of diamonds. So if we go back to the card deck here, come on. 5 of diamonds is this card right here. So there's only one 5 of diamonds. That's the wrong one. Here, come on. Here we go. So there's only one 5 of diamonds, and that's out of 52. Okay, next one is the probability of a black card. If we go back to our card deck here, we can see that these 13 cards are black and these 13 cards are black. So 13 plus 13 is 26 out of 52, which is a half. simplifies to a half. Okay, next, the probability of a diamond. So we have 13 cards in diamonds out of the 52. This simplifies to 1/4. Next, it's going to ask us king or club. So this one here, if we go back to our card deck here, and let me actually erase some of this now so that it's a little bit easier. Um, so the question was king or club. These are our no, sorry, I'm circling the wrong one. These are our clubs, and these are our kings. Now notice that there's a king of clubs that we circled twice. We need to make sure that we don't do that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 cards. So what I meant to say that we don't do that, we don't count it twice. So notice that this would be 16 cards. If we just added the number of clubs, that's 13, and the number of kings, that would be 4, this would be 17. With this number, we've counted the king twice because it's part of this and part of this. So what we need to do is subtract that king once away, and we get the same 16 as we got when we counted the cards. Okay, so king or club would be 16 out of 52, which um, simplifies to 4/13. Next, we have king and club. So notice the word difference between the or and the and. Now, when we have a king and a club, that means that we are only talking about this card because that's the only card that is a king and a club. So this one is 1/52. The probability of an ace, we have 4 aces out of the 52, so this simplifies to 1/13. As you can notice that there's a lot of the same simplified fractions on here depending on what we're talking about. Ace of spades, again, there's only one ace of spades, so that is the 1 out of the 52. Okay, next one. The probability of a 5 or a 10. So how many 5s and 10s do we have here? We've got, all of these have, we've got 5s, so this is 4, and here are 10s, that's 4. So 4 plus 4 is 8. So 8 out of 52, and that simplifies to 2/13. Now, our next question is 5 and 10. Well, is there a card that has a 5 and a 10 on it? No. So this probability is going to be a 0. Next one is the probability of red. Well, half the cards are red, so 26/52, which does simplify to a half. You could just write the half. You don't need to necessarily do this. So there's 13 diamonds and 13 hearts. 13 plus 13 is 26. Okay, next one. Um, the probability of a heart. Well, there's 13 cards in hearts out of the 52, which gives us 1/4. Red or black? If we look at our cards here, do we have any other cards other than red or black? No, we don't. So all the cards are either red or black. So that means that this is going to be a 1. 52 out of 52. Same thing as 1. Probability of red and black. Again, notice the difference. There's an or and here's an and. Well, is there a card that is red and black? Nope. So that's going to be a 0. Okay, next, um, we're going to look at a fair coin that is tossed 2 times in succession. So a fair coin means that we've got um, the option when we toss the coin, the outcomes can be heads or tails. Now we're tossing it twice, so this is our first toss. Our second toss, if the first one was heads, we can, for the second one, get heads or tails again. If the first one is tails, we can get a heads or tails again. So our sample space here would be, actually, let's write an organized list first. So we're going to look at these two. So that's heads and heads. Oops, that looks like H and H. This one is H and T. Here we have T and H, and this one is T and T. So this is an organized list. You might see it vertically written a lot of times like this because of the way I did our tree. It was easier to write it down here. So that is our sample space for this one. So we have heads and heads, we have heads and tails, tails and heads, and tails and tails. Okay, let's go ahead and look at these probabilities. So, probability of 2 heads. Well, there's only one that has the 2 heads, so that's 1/4. Next one, 2 tails. Well, the same thing. There's only one that has the 2 tails, so that would be 1/4 also. Next is same outcome. So this means that it doesn't matter what order they are, it's just the same outcome, which means that heads or tails or heads, the outcome is the same. We have 1 heads and 1 tails. So we have 2 out of 4, which simplifies to a half. Next one is different outcomes. So our different outcomes would be the heads and heads and tails. So 2/4 is going to be a half again. Next, head on second toss. So here's a head on second toss, and here's a head on second toss. That's 2 out of 4 again, which is a half. Our last one is at least 1 head. So at least 1 head is this one, and this one. So 3 out of 4 would be at least 1 head. Okay, let's look at geometric probability. So we have a spinner shown at the right that has 4 sectors labeled. So we've got our red. We have, this is going to be my yellow, even though it looks more orange. Then we have our green and a blue, and I can't color inside the lines. Okay, so next question. What is the sample space for this experiment? Well, our sample space is going to be red, yellow, blue, and green, right? Those 4 colors. Since the blue sector is 1 out of 4 equally sized sectors, the probability that the pointer will land on blue is going to be 1/4. Again, 4 equally sized. Find the theoretical probability for the pointer landing the given color for each of the following. So first one is green. Again, that's going to be 1 out of 4 because we've got one green and it's out of the 4 different colors. Next is going to be yellow or green. So we have 1 and 2 that are going to be yellow and green. So 2 out of 4, which simplifies to 1/2. Not red is all the others except the red. So we have 3 because we've got the yellow, blue, and green out of 4. Okay, this next one here, it has a spinner that has 3 sectors labeled. So we have a blue, we have a green, and we have a yellow. An experiment consists of spinning the pointer once and recording the color. So, are the events blue and green equally likely on the spinner? No, they are not. The blue is twice as big as the green sector. So that is not. So imagine dividing this spinner into 4 sectors as shown at the right. So here we can see that blue has been divided to 2. Then we've got the green and we've got the yellow. So explain how this can help you compute each of the following probabilities. Well, this helps us see that there's 2 blues that are the same size as the green and yellow. So this would be 2 out of 4, which is 1/2. I mean, we can see that this is 1/2 of the circle. But again, if it's not this clear, it helps us that since they are the same, we can count how many of them there are. Okay, next one is blue or green. So 1, 2, and 3. We have 3 same sized and 4 out of all. Again, we need to count how many same sized we've got in order to get tell the probability correctly. Okay, we're going to use a similar technique to do what we just did to find the following probabilities for the spinners shown at the right. So what do we have here? We have a blue and we have a blue. We have a yellow and a green. Well, these are all different colors, different sizes. So what we need to do is we need to split this into the same sizes. So we can draw a line through here. So we see that there's 2 greens, and we can draw a line through here and split that blue again. So now the probability of a blue, we've got 1, 2, and 3, same size. So 3 out of the 6 that we have, we've got 1, 2, 3, 4, 5, and 6, which is simplifies to 1/2. Probability of a yellow, well, there's 1 yellow here, 1 out of 6. Next, we have yellow or blue. So we have 1, 2, 3, and 4, yellow or blue. So 4 out of 6, which simplifies to 2/3. Probability of not green. So there's 2 ways we can do this. We have 2 greens, and we can do 1 minus 2/6, which is 6/6 minus 2/6, which is 4/6, and that simplifies to 2/3. Or we could just count 1, 2, 3, and 4 are not green and say that 4/6. Now, I don't know if I talked about, the fact that we do give these in the probabilities in fractions or decimals or percentages. If they are fractions, make sure that you simplify. Again, your calculator, the fraction button will simplify it for you. If you plug in 4/6 and hit enter, it will give you 2/3. Okay, that's it for this lesson. Let me know if you've got any questions. Bye.